Modern electric vehicle powertrains demand massive energy to accelerate to highway speeds, requiring systems that instantly draw hundreds of kilowatts from a battery pack. We rely on lithium-ion batteries to supply this power because of their exceptional energy density. However, that density comes with a stark physical reality. The chemistry inside these cells is intrinsically unstable. A single lithium-ion cell operates safely only within very narrow physical parameters. If it gets too hot, too cold, or if energy is pulled from it too quickly, the internal chemical structure degrades. Pushing a cell past these limits causes a rapid exothermic reaction called thermal runaway. Pressure builds and the cell violently vents heat and particulate matter. In a densely packed environment like a vehicle chassis, the extreme heat from one venting cell quickly transfers to its neighbors. A single failure cascades rapidly, engulfing the entire pack. To harness this chemistry for a vehicle, every cell must be contained within a precise safety envelope. Without a system to enforce these boundaries, high-performance power is inseparable from the risk of failure. Cell manufacturers define exactly what that safety envelope looks like. This 3D Cartesian graph plots the three critical operating axes of any lithium-ion cell: voltage, temperature, and current. The smooth, curved volume in the center represents the cell's baseline safe capability. If a charging source forces the cell's voltage past its maximum threshold, the electrical pressure damages the internal structure. Likewise, if the ambient temperature exceeds safe limits during operation, the chemical components inside break down and generate hazardous internal heat. And if the system draws or pushes current at a rate faster than the chemistry can accept, the resulting internal resistance forces the cell outside its safe parameters once again. To prevent any of these conditions, the entire battery pack is governed by a dedicated electronic architecture, the Battery Management System, or BMS. The BMS continuously tracks voltage, temperature, and current. It maps those values in real time to mathematically define the exact boundaries of the cell's safe operating area. By actively restricting the system from ever breaching those mathematical boundaries, the BMS imposes strict order over volatile physical chemistry to ensure reliable operation. A single cell only produces a few volts. To generate the hundreds of volts required by a modern powertrain, we have to physically connect multiple cells together. This schematic illustrates the simplest multi-cell electrical architecture, a 3S1P configuration. 3 individual battery cells wired end-to-end in series. Connecting cells in series combines their total voltage, but it also obscures their individual status. The system can easily read the total output of the chain, but a single failing cell hidden in the middle could still trigger thermal runaway. Therefore, the first systemic requirement of a battery pack is high-fidelity analog measurement, mapped specifically to every individual cell. This task is handled by the first physical module, the Cell Monitoring Unit, or CMU. The CMU relies on specialized analog front-end integrated circuits. These chips attach directly between the individual cells to pull continuous, highly accurate voltage and temperature readings. Because analog signals degrade over distance, these circuits must be physically mounted as close to the battery cells as possible to ensure the data is pristine. This proximity creates an engineering hazard. A sudden voltage spike from the high voltage paths could destroy adjacent measurement hardware. To solve this, the CMU passes collected data through isolated communication channels. These galvanic barriers physically block high voltage current from crossing over. This isolated analog measurement is the primary input for every safety calculation that follows. If the data from the cells is inaccurate, the entire system's ability to prevent thermal runaway is compromised. While the CMU provides microscopic visibility into every individual cell, the system also requires macroscopic context of the pack as a whole. That macroscopic data is captured by the second physical module, the Battery Junction Box, or BJB. The BJB's primary data acquisition role is measuring the total magnitude of current flowing into or out of the complete system. This vector diagram illustrates one method for measuring this, placing a shunt resistor directly in line with the main high-voltage wire path. Because the shunt has a precisely known electrical resistance, measuring the slight voltage drop across it calculates total current. An alternative method relies on non-contact Hall effect sensors. Instead of an inline resistor, a sensor ring simply clamps around the exterior of the cable. As high voltage current travels through the unbroken wire, it generates a proportional magnetic field. The Hall effect sensor measures that field, calculating the exact current without ever touching the actual circuit. Without macro-level current data provided by the BJB, the system cannot accurately judge how quickly the entire battery pack is being depleted or recharged. At this stage, the system has gathered massive amounts of raw analog data, but that data requires processing to be useful, which is handled by the third and central module, the Battery Management Unit, or BMU. The BMU acts as the brain of the architecture, running complex algorithms to contextualize the incoming voltage, temperature, and current readings. This block diagram maps how those inputs flow into the processor. The first critical algorithmic output is the state of charge. Total remaining energy cannot be directly measured by any physical sensor. Instead, the BMU algorithmically estimates state of charge, functioning as the system's fuel gauge. Simultaneously, it calculates a second output, the state of health. Over its lifetime, the internal chemistry of a battery degrades. The state of health algorithm tracks this degradation by comparing the pack's current storage capacity against its original baseline capacity when brand new. By cross-referencing the state of charge against the degraded state of health, the BMU continuously calculates a dynamic, safe operating envelope, setting hard mathematical limits on current flow in real time. The BMU serves as the translation layer, converting raw analog sensor readings into precise digital constraints. Calculating limits is only half the job. The BMS must have a way to physically intervene if the battery breaches those limits. This physical intervention relies on heavy-duty, high-voltage contactors, mechanical relays physically housed back inside the battery junction box. If the BMU detects a severe fault condition, like a sudden voltage spike or rapid temperature increase, it triggers these contactors to physically snap open, instantly severing the connection between the battery pack and the outside circuit. Beyond emergency safety protocols, the BMS also executes routine physical interventions to optimize performance. This bar chart represents 3 individual battery cells holding unequal amounts of charge. Over time, the BMS performs active and passive cell balancing, intentionally redistributing or burning off small amounts of energy from the highest cells until the entire pack achieves a perfectly uniform voltage. Whether opening emergency contactors or balancing microvoltages, these mechanical and electrical mechanisms serve as the physical enforcers of the mathematical limits defined by the BMU. The logic governing a simple 3-cell configuration must be replicated and synchronized thousands of times to meet the demands of a high-voltage vehicle. A complete 800 volts automotive powertrain distributes this exact topology: local cell monitoring units, a central battery junction box, and an overarching battery management unit across thousands of lithium-ion cells. Managing an architecture of this scale requires extremely rigorous safety standards, such as ASILD certification, to ensure that component failures do not compromise the logic of the entire system. Once safely constrained, the final requirement is integrating it with the vehicle through an external communications interface. The BMS utilizes this interface to broadcast real-time operating parameters and fault statuses outward to application controllers, like the electric motor and power inverter. These external systems rely entirely on the data provided by the BMS to safely adjust their behavior, throttling motor torque or limiting regenerative braking based on exactly what the battery can mathematically handle in that specific millisecond. We began with highly reactive physical chemistry, materials that will violently expand if pushed past their natural physical constraints. The battery management system enforces digital constraints on physical chemistry, allowing us to deploy this high-density energy storage while maintaining the safety and reliability required for the road.